Everyone, today we'll be discussing about electrophysiology. In this, we'll talk on membrane potentials, and then later we'll be talking about resting membrane potential and its genesis. Membrane potential. Membrane potential is refers to as charge separation across the cell membrane. So here you can see this is a cell and this is the cell membrane. There is a charge separation with inside being negative and outside being positive. So membrane potential refers to separation of opposite charges across the plasma membrane or cell membrane. It is measured in millivolts. Resting membrane potential. Resting membrane potential is defined as the membrane potential across the cell membrane during rest, means when the cell is not stimulated. So when the recording microelectrode is kept on inside of the cell membrane and reference electrode outside, the membrane potential recorded is minus 70 millivolt, and this is the resting membrane potential. During this, the cell is not stimulated. Resting membrane potential is shown by both excitable and non-excitable cell. So excitable cell neuron shows the resting membrane potential value minus 70 millivolt, skeletal muscle shows minus 90 millivolt, and cardiac muscle, that is ventricular cardiac muscle, shows minus 90 millivolt. Now why resting membrane potential of an excitable cell is always negative? Now let's discuss about this. So there is a difference in ionic distribution intracellularly and extracellularly, plus there is also a difference in relative permeability for different ions. Sodium is more extracellularly with 150 millimoles per liter, intracellularly 15 millimoles, and relative permeability is only 1. Potassium extracellularly 5 millimoles per liter, and intracellularly it is very high, 150 millimoles per liter, while the relative permeability for the potassium is 70 to 100 times. Anionic molecules like phosphate and proteins, it is extracellularly 0 and intracellularly it is 65, while it is impermeable because relative permeability for anionic molecule is 0. So this shows that the nature of the cell membrane is very permeable to potassium ion, less permeable to sodium ion, and impermeable to anionic molecules. Besides, the equilibrium potential of sodium ion is plus 61 millivolt, potassium ion is minus 90 millivolt, chloride ions is minus 70 millivolt. Of concurrent potassium and sodium movement on establishment of resting membrane potential. Intracellular potassium is high. The nature of the cell membrane is very permeable to potassium ion, so relatively large net diffusion of potassium outward establishes an equilibrium potential of potassium, that is minus 90 millivolts. While anionic molecules is impermeable, so there is no net diffusion of anionic molecules across the cell membrane. While sodium ion being more outside, and then relative permeability of the cell membrane towards the sodium is less, so there is a relatively small net diffusion of sodium ions inward and neutralizes some of the potential created by potassium alone. Resting membrane potential is close to equilibrium potential for potassium ion and chloride ion because the permeability to these ions is high during the resting state. So final contribution to the resting membrane potential is by electrogenic pump, that is sodium potassium ATPase pump, which pumps the 3 sodium out of the cell and 2 potassium is pumped towards the inside of the cell with the utilization of 1 ATP. However, this electrogenic pump only accounts for minus 3 to minus 4 millivolt of total resting membrane potential. So it's a minor role. So with this we come to the end of today's discussion on membrane potential and resting membrane potential. Thank you.